Okay, X5 motion in 3D. X of t is the position vector of a particle at time t. Compute the velocity and acceleration. Velocity is the first order time derivative of the displacement vector, and we find the difference of the position vector, that is the displacement from time t to t plus h. It's divided by the time difference h, and we take the limit as h goes to 0. That is the velocity. And we take another time derivative, that is the second order time derivative, that is the acceleration. And when we compute the acceleration, we can take the first order derivative, or this one can be expressed in terms of this and this. And why don't we substitute t plus h in here? Then it becomes t plus 2h and t plus h. So argument will be shifted in here, and we need to subtract it measured at time t. If we expand everything all together, we have h squared in the denominator, and the numerator becomes t plus h, and t plus 2h. And we have a sign difference, a minus. So as you can see, the coefficients are binomial coefficients. And for example, a plus b squared equals a squared plus 2ab plus b squared. And if I substitute minus b instead of b, this expansion formula is x squared minus 2ab plus b squared. These coefficients we call the binomial coefficients, and we take the negative sign, so sign flips, plus minus, and so on. So second order derivative can be directly computed from the function itself. You could have defined the derivative, for example, t plus half of h subtracted by t plus minus half of h, and the difference is h. Or x of t subtracted by x of t minus h divided by h. Everything is the same. In a similar manner, I can shift this h by minus h, minus h, minus h, and minus h, and we can find the symmetric form x at t plus h subtracted by twice x of t, and add the value at x minus h. So this second order derivative can even compute it directly from the function itself. We know Leibniz rule for the product function, and that is very useful to compute the product of a scalar and vector. And this is arbitrary scalar depending on time, and we have a vector as time derivative. You must have known that take the derivative of the first factor and take the derivative of the second factor, sum them all. In general, a position vector is a linear combination of the unit basis vectors, and the coefficients are x1, x2, and x3. And these Cartesian basis vectors are independent of time, and only the time dependence appears in the components. If I take the derivative, it is a sum of three components. And if I take the derivative, use Leibniz rule. And if I take the product, derivative of the product, the derivative. By the way, these unit vectors are independent of time, so this one vanishes. The only thing is the derivative of the coefficients, that is the components. As a result, the velocity can be simply computed by taking the derivative of components and sum them all by weighting the unit basis vectors if we make use of Cartesian coordinate system. So Cartesian coordinate system is very useful. And in a similar manner, I can take the derivative of the scalar product, and the same rule applies. Take the derivative of the first vector and second vector and sum them all. You must have known that the scalar product is a sum over I that runs from 1 to 3. A vector is AI hat. So in here we should include all of the components, but it is very compact to write this kind of form. What happens if I have both A and B are the same? In that case, it is trivial. These two terms becomes the same. We have 2 times derivative of A, scalar product, and A. This one appears when we compute the kinetic energy of a particle, the time derivative of the kinetic energy of the particle. So we have 1/2 mass is constant in non-relativistic theory, and we take the time derivative of this guy. We substitute A equals x vector dot. So velocity. Velocity squared, we have taken the time derivative of the velocity squared. We use this formula, then the result is a factor of 2, second of the derivative, that is acceleration, and then first of the derivative. So what's that? Mass times acceleration, that is a force. So force times velocity. This times is a scalar product. We call it power. And power is actually x dot equals velocity times time. So this is velocity and displacement divided by time. So it is f dot dx over dt. Okay, so this is work. Work per time is called power. We can apply the same method to compute the time derivative of cross product of 2 vectors. Derivative, sum them all. We will find this application very soon. We substitute x and mx dot, that is mass times velocity, that is the linear momentum. So x is the position, cross product, linear momentum. It is called L, and it is called the orbital angular momentum. Time derivative of the orbital angular momentum is this. We have cross product, take the first time derivative of the first vector, that becomes velocity. Time derivative of the second piece, that is mass times acceleration, that is force. However, in here, we have x dot cross x dot. Same thing, cross product always vanishes. So this is x, the same x, cross product, and force. It is called torque. And that is actually time derivative. X cross p is called orbital angular momentum, is x cross force, that is called torque. This is the rotation version of Newton's second law. The position of a particle is given like that. So radius times unit radial vector. Unit radial vector is nothing but a point or a circle of radius r. This is a radius and this is tangent. And radial vector is product of radius and unit radial vector. And where r radius, oh, this is not a circle. Radius can vary. So this radius is depending on time. Okay, so, and then we have a unit radial vector and we have a perpendicular vector. This one, they are perpendicular. Any tangent to a circle is always making a right angle to the radius. And we take the direction increasing the angle theta. So unit tangent vector can be expressed in this way. So simply we can translate into one to make another radius that is making a right angle with respect to the original radius vector. So this is original radius vector that is proportional to ER hat, and this is tangent vector shifted to the center. So we call it E theta. And we know this one, they are perpendicular to each other. You know, cosine, sine, scalar product minus sine, cosine. If you multiply minus sine, cosine, cosine, sine. Okay, exchange the xy coordinate and put the negative sign. Always these two vectors are perpendicular to each other. Anyway, we use this. We take the derivative of the unit radial vector. And we know these Cartesian basis vectors are independent of time. Only the cosine theta can depend on time. However, they are depending on time indirectly through theta. So we can make use of chain rule. So cosine theta's time derivative is first take the theta derivative of cosine and then multiply the time derivative of theta. So we know this is minus sine and this is a theta dot. So minus sine theta dot minus sine and theta dot. Here, this guy becomes cosine theta dot. So we find that the coefficient of theta dot is nothing but the unit tangential vector. So we can rewrite this one as a theta dot multiplied by E theta. If they are making a right angle, ER time derivative is E theta. So rotate by half a pi counterclockwise. What happens to the time derivative of theta? E theta's time derivative again rotates by half a pi in this direction. Oh, what's that? This is opposite to the original unit radial vector, minus. Therefore, E theta dot, eventually you find negative sign on it, and theta dot, and this. So theta dot's time derivative is minus theta dot, E theta's time derivative is minus theta dot ER. In this manner, I can take second order time derivative of unit radial vector. So if I take the second order time derivative of this guy, that this first order time derivative ER is a first order time derivative. And we copy this result in here, and we apply Leibniz rule. And this derivative, because double dot, and then we take the derivative. So keep this one as it is, and we take the derivative e theta, and then this is copied, and what's that? This gives minus theta dot er, minus theta dot. So we have flipped the sign, and theta dot was there. I have another theta dot to have a theta dot square and radial vector. As a result, Leibniz rule is very convenient to find the general form of the acceleration on the two-dimensional plane. That is, general two-dimensional vector is a radius multiplied by unit radial vector, second order derivative of this. However, second order derivative of this. So we have a product. So R has a double derivative, single derivative, no derivative. If there is a double derivative, ER has no derivative. If R carries a single derivative, this guy has a single derivative. This guy does not have derivative, then ER has a double derivative. I can copy all of these resulting in here and simplify everything altogether. In that case, we obtain radial part, and tangential part. They consist of two terms, radial and tangential. And here, this is a radial acceleration. We have negative minus r theta dot square, that you must be familiar with r omega square. Minus r omega square is the centripetal acceleration. And we have r theta double dot, that is a tangential acceleration. Tangential acceleration is if you spin a top, spinning a top, that you hit it, and give the torque to make it rotate faster. So this tangential acceleration is due to the torque, and there is a strange term, radial velocity multiplied by the angular velocity. This is called the Coriolis contribution. You know, the wind blows from the high pressure to low pressure directly only if there is no rotation of the Earth. In fact, from high to low on the northern hemisphere of the Earth, wind blows in this direction, not straight, because of Coriolis acceleration. Okay? Acceleration of a particle is given by like that. Okay. The position of the particle. Position, okay. If I move this guy, we have x of t minus x of 0. What's that? It is identical. This is by definition change from some point to another is from some point to another integral of the derivative. What's that? Time derivative of x integrated over t. But let's see. So upper limit, lower limit, they are copied, but we have the dummy variable. Therefore, we need to distinguish this integral variable and upper and lower limits. So I have attached prime in here. For simplicity, if I increase the number of integration, it is convenient to attach this differential to the integral sign, because if there are many integrals, it is a very difficult to distinguish A, B, C, D, E, F, then I don't know what upper and lower limits corresponds to what differential. So if I write in this manner, there is no way of mistaking. Okay, we do not have to be confused. So this form is not good for multiple integration. This way is easy to identify. Okay, we follow this rule to find out the expression for the position of particle, satisfy this equation of motion. This is constant acceleration. So in here, difference, definite integral of the velocity. Okay, that's fine. And what's that? This is the second of the derivative is constant. So if I take the time integral prime 0 to t, then a vector 0 to t dt prime. So what's that? This trivial integral a times t. So let's find in here. Let's see. I have made a mistake. There should be prime in here. So I can substitute the difference between the initial value and the change. Okay, I substitute this result in here to find that. Finally, I can repeat the integration. The final result is this. By the way, we noticed that initial position vector and initial velocity vector, they are unknown. This equation does not know, we do not know what these values are. So these two vectors are free vectors. So they should be determined by some measurement or initial conditions. In here, you have found that this t is actually expressed as integral from 0 to t, and we have attached prime. Therefore, we have 0 to t dt prime, t prime substituted here. So prime, prime, double prime. In that case, this guy is replaced with the right-hand side. So we arrive at the double integral. Okay, so this is given in here. We have found that this one is actually, if you carry out this integration, that is 1/2 t squared. So double integral, this double integral is 1/2 t squared. So we like to know what happens if I increase the number. In here we have considered 2. We do not know whether it is, if I increase the one single power, is it t cubed or 3 factorial in the denominator. This shows that, according to mathematical induction, it is not 1 over n, but 1 over n factorial. You can repeat this step by step in a straightforward manner.